Okay, so like I was saying earlier, we start out with 100% probability. We break that in half. We have 0.5, 0.5 for heads and tails. That's our first toss. Second toss, we have heads and tails again. We have to cut our 0.5 in half again, so we divide by 2. When we divide by 2, we get 0.25. So we have a 25% chance of flipping heads, heads, 25% chance of getting heads, tails, and so on. When we flip the coin 3 times, we have to cut our 0.25 in half again. So we divide 0.25 by 2, and we get 0.125. So this is my probability of flipping heads, 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 all in a row. So here's our probabilities for that. So let me write these out, our outcomes. So our first outcome is heads, heads, heads when we flip 3 times. Heads, heads, heads. Next one is heads, heads, tails. Next one is heads, tails, heads. Next one is heads, tails, tails. Next one is tails, heads, heads. Next one is tails, heads, tails. Next one is tails, tails, heads. Last one is tails, tails, tails. So those are the 1, 2, 3, 4, 5, 6, 7, 8 outcomes we have when we flip the coin 3 times. So here we can do a lot of different problems with probability. So for instance, if I asked you, what is the probability of getting 2 heads in any order when we flip the coin 3 times? We can do that really simply. So we're going to look for each of these iterations that has at least 2 heads. So let's see here. Does heads, heads, heads have 2 heads? It does. So that's that one. This one has 2 heads as well. This one has 2 heads as well. That one doesn't, so we don't count it. This one does. That one doesn't. That one doesn't. That one doesn't. So we've got 4 iterations where we have at least 2 heads occurring. So how you would find that probability is go 0.125 times 1, 2, 3, 4. And when you do that, it should be 0.5, right? Yeah, 0.5. So you have a 50% chance when you flip the coin 3 times of getting at least 2 heads. So that's how you would do that type of problem. What if I were to ask, what is the probability of getting tails at my 3rd try? So we're going to look to see which one of these iterations has tails in the last position. So this one does not have tails in the last position, so it's out. This one does have tails in the last position, so it's in. This one doesn't, so we don't count it. This one does. That one doesn't. This one does. This one does. So again, we've got 1, 2, 3, 4. 0.125 times 4. We have a 50% chance, or 0.5% chance, or 0.5 chance of getting tails in our last flip when we flip the coin 3 times. What is the probability of getting tails, tails, tails? We see that that is 0.125 or 12.5% chance. So that's how you would do a problem like that. You can either add them up or you can multiply, whichever works best for you. So those problems aren't too difficult, but if you have questions on them, please email me and we can help you out. So now let's return back to our PowerPoint. So again, we are on slide 12. So here's another example of our binomial distribution. How often do two heads appear together in a sample? So I'm pretty sure that was the one I did earlier. So you would just go and you would find how many of our iterations have two heads, then you would add those all up to find out the probability. You can also express a probability in ratio like this with the colon. So this kind of interprets what that means. So if you've got a 5-to-1% probability or 5-to-1 ratio probability, that means that there are 5 ways to fail, 1 way to succeed. 2-to-3 odds means that there are 2 ways to fail, 3 ways to succeed. So that's another way to express that. Again, we have a Mark Wahlberg meme here. This is a really important point. So I talked earlier about how we have our theoretical and our empirical distributions, and that when they overlap, this is good for us because we can come up with probabilities. However, it's really important to note that our theoretical distributions might not always be exactly the same as our empirical distributions. So our empirical distribution may not always reflect what will actually happen in real life when we actually obtain data from the real world. Because it's using math and probability and logic, it's not always going to be exactly the same as how it will play out in real world. So it's important to keep that in mind. Rather than giving us what's actually going to happen, it's going to give us the best estimate of how events will actually occur. A theoretical distribution is one based on logic and math rather than actual observations. It gets pretty close, it does a pretty good job, but it's not going to be 100% accurate all the time because it's estimating. Now we're going to go to the normal distribution. We've talked a little bit about this in the past. We're going to continue on with it. So normal distribution is a bell-shaped theoretical distribution that predicts the frequency of occurrence and chance events. So here's a lovely picture of our normal distribution. We see that 68.2% of the distribution, so a good proportion of it, of people on a given trait or whatever, fall within 1 standard deviation from the mean. So let's take IQ, for example. So IQ is distributed on a normal curve like this. So what that's saying is 68.2% of the distribution have an IQ that is at least 1 standard deviation from the mean, either above the mean or below the mean. If we go out farther to 2 standard deviation units, we see that even more people fall within that range. So 95.4% of the distribution either score within 1 or 2 standard deviation units, either above or below the mean. And almost everyone, not everyone, but almost everyone, falls within 3 standard deviation units from the mean. So 99.7% of scores on a normal distribution fall within 3 standard deviations from the mean. So some more characteristics of the normal distribution. It's symmetrical, it's bell-shaped, theoretical, based on math formulas rather than empirical observations. However, your empirical data can also fall on a normal curve, and we actually want that to happen because then we can derive probabilities of our events occurring because there is that overlap between our empirical and theoretical distributions. So here we have an example of our z-score formula, which we learned in Chapter 5. We can actually use this to derive probabilities. So say that we get a raw score, our x, we convert it to a z-score, and then we use what we call the z-table to then come up with probabilities of obtaining that z-score. So I'll show you how to do that in a few slides. Here's some more vocab words. These are not super important. They're just in your textbook. They might be in your quiz. That might be something to star for the quiz, but it won't be on your test. It's not super important. So this is basically some descriptive words about the normal curve. So the normal curve is asymptotic. That's that first word there. So what that means is that our edges of the curve continually approach but never reach the x-axis. So you see here they're really close, but they never intersect with the x-axis, so it's asymptotic. And the normal curve also has an inflection point, and that's a point on a curve that separates from a concave upward arc, so upward from a downward. So this is our inflection point here. Again, these are just some descriptive terms that are not super important, but might be helpful for the quiz. Another picture of inflection points. Again, here's our normal curve with our probabilities associated with it. So here we're talking about converting our z-scores from regular scores, from raw scores. So converting empirical distributions to the standard normal distribution. So this is when we have our raw data from an empirical distribution and we use our theoretical distribution, the normal curve, to come up with probabilities. So we do this by converting our raw data into z-scores. And as a review, the mean of our z-distribution is always 0, and our standard deviation units move in units of 1. So you see here, mean 0, we move in units of 1 away from the mean. So here is a screenshot of our z-distribution. So we've got a lot going on here. This is the table that we use to come up with probabilities for our events, for our raw data. So a few things to keep in mind. We've got 3 columns that we're working with here. We have an A column, we have a B column, and we have a C column. Our A column is where we have our different z-scores. So we start with the z-score of 0, which we know is our mean. That falls right here. And we go down, and it continues and continues and continues to about 4 or 5, I believe, is the highest z-score that is on the table. Column B tells us about the points on the distribution. Let me draw this out so it makes a little more sense. Column B on the z-distribution gives us the probability of an event, or probability of a z-score rather, between the mean and a given z-score. So we use our column B, so say we're looking at a z-score of 1. So say we are interested in what proportion of the distribution falls between the mean, or 0, and 1. We would use our column B there, our mean to z column. So let me shade that in. So for problems that ask you what the proportion of the distribution, or what probability is associated with a given z-score to the mean, you're going to use your mean to z-score, your mean to z column rather, or column B. So column B gives us the probability, or the proportion of the distribution that is associated with the given z-score to the mean. So it tells you the distance between your z-score and the middle of the distribution. So that's what column B does. So it's more concerned with, generally speaking, the column B is more associated with the middle of the distribution because it's working with the mean. So most of the time, if you're interested in the middle of the distribution, you're going to be working with column B. You're going to be working with mean to z. So that is column B. Column C, on the other hand, is when we are interested in the extremes of the distribution. It's going to give us the probabilities from z to infinity. So say I was interested in what proportion of the distribution is associated with a z-score of 1.1 or higher. So 1.10. So this is the z-score that we're working with, 1.10. So say I was interested in what proportion of the distribution is associated with this score or higher. That means that I'm interested in our tail of the distribution, the edges. So I'm interested in this shaded piece here. So if that's the case, if that's what our problem is asking us for, the edges, we're going to use our z to infinity column, or column C. Z to infinity. So in this case, what proportion of the distribution is associated with 1.1 or higher? Our answer for that would be 0.1357. And if you wanted to convert that to a percent, you would just say 13.57% of the distribution is associated with the z-score of 1.1 or higher. Or another way to say that is 13.5% of z-scores are 1.1 or higher. So that's how you kind of work with the z-table. So like I was saying earlier, if our question is asking for the middle of the distribution, the top of the curve, if you will, you're mostly going to be using our mean to z column, so column B. If you're more interested in the edges of the distribution or the extremes of the distribution, then you're mostly going to be working with column C, or your z to infinity column. So let me go ahead and pull up a full example of our z table. So this is the z table that I have posted on Moodle. It's also in the back of your textbook. This is what it looks like. So it ranges from 0. When we go down this column, we see that it goes to 0.54, and then it continues to 0.55, yada, yada, yada. It's 2 pages. We see that the highest z-score that it goes to is 4, which makes sense, right? Because what I said earlier was that 99.9 or 99.7% of z-scores fall within 3 standard deviation units from the mean. So here we're getting into some real extreme values at the 4 z-score level. So here is how you read the z-table. So say that we are interested in what proportion of the distribution is associated with with 1 or higher. We'll say 2. We'll say 2 because we already did 1 earlier. So say a problem asked you, what is the probability of obtaining a z-score of 2 or higher? That's asking you for the edges of the distribution. That's asking you for this. So that means we're going to be using our z to infinity column, our column C. So we look here, we look for 2, we look for our z-score of 2, we see that here in our z column, or column A. So here's our z-score of 2, and we see that the probability that's associated with that, our z to infinity column, tells us that the probability of getting a z-score of 2 or higher is 0.0228. If you wanted to convert that to a percent, it would be 2.28%. So that's saying that 2.28% of scores on the normal distribution are 2 or higher. So I also have some practice problems posted, doing some more of this, getting into some more nuance of that So definitely make sure to watch that video as well. So let's go ahead and jump back into the PowerPoint to make sure that we cover all of that. So here's your slide of your Z distribution. That is slide 26. So now let's move on to slide 27. You can find your Z table on Appendix C, page 400 in your book. Here is your Z formula. We talked about this in chapter 5. This is just a review of it. So here's how you find a Z with population information. Here's how you find a raw score given your Z score. So that's how you convert. You can also find the proportion of the population between two scores, and I have an example like that in your practice problems video. So make sure to watch that. It's towards the end. So you can also do that as well. So for example, you can find and I say in the other video as well, make sure that when we're doing these kind of problems that you always draw them out so that you can see what's happening. I think it's a lot easier, especially when you're first learning how to do this, to draw everything out so that you see what's going on, and then for the projects and everything in the test, I can see what's happening, especially if you make an error, I can see where you went wrong. So make sure to draw it out. For example, you can find what proportion of the distribution falls between like -1 and +1. You can do that type of problem as well. And you would do that by just finding the value for mean to Z for 1. So the prompt for a problem like this would say something like, so the question for something like this would be, what proportion of the normal distribution falls between a Z-score of -1 and +1? And I drew that out here. The middle, we always have 0. Your mean is always 0 for the Z distribution. Here we've got -1. On the left side, I've colored in the space between -1 and 0 in red, and then I've colored in the space between 0 and +1 in blue. So in order to do a problem like this, you would look at your mean to Z column, or your column B, and find the probability of that. You would want to find the probability of the red space, and then add it to the blue space, and that would give you your answer. So we're going to find mean to Z for 1. And this is a really good example because it illustrates that our Z table does not have negative and positive. It's in absolute value. And the reason that that is because the normal distribution is symmetrical. It's a mirror image of itself when it's cut in half. So regardless of whether you're talking about the negative side or the positive side, your probabilities are still going to be the same. So let's go to the Z table and show you what I'm talking about. Okay, my computer's freezing. So if we go to a Z-score of 1, is down here. So if we look at our Z column, column A, we follow it down to find 1. And remember that we are looking for our mean to Z, which is our column B, which we find here. We see that the probability of that is 0.3413. So 0.3413 is the red space, and it's also the blue space, because it's still 1 standard deviation away from the mean on either side. So then you add those two together. Make sure that we can still see this. When you add those two numbers together, 0.3413 plus 0.3413, we get 0.6826. So we can find the probability between two z-scores by using that mean to z column like that. So let's go back to our PowerPoint. We're almost done with this. So that's how you would find the proportion between two scores. These next two slides are really important, so make sure to make some notes with these. So extreme scores in a distribution are important for many statistical procedures. We care about the ends of the distribution. We care about the tails because those are the extreme scores, and those really matter to us. For many applications, the focus is on 5% of the distribution. So it's on, we like to focus on the 5% extreme. That's really important to us because it's what we call statistically significant from the rest of the distribution. So let me write that out. So we really care about the top 5% of the distribution. Well, let me do that again. So we really care about our extreme scores. Some instances we might care about when our scores fall in the extremes on the right end of the distribution. We might also care when our extremes fall on the left side of the distribution. But oftentimes we also care about when they fall on both sides. And when that happens, when we care about both sides of the distribution like that, it's called two-tailed, which we'll talk more about in chapter 9. But when we do care about both sides of the distribution like that, we have to cut this 5% in half. And when we do that, we get 2.5% on each side. Ooh, not very even. .5%, 2.5%. So when we care about both sides like that, we have to cut the 5% in half to get 2.5% on each side. When we cut 5 in half, we get 2.5. So 2.5% on each side. So if you were to look at your z distribution to see what z-score is associated with 2.5%, that is 0.25%, we see that that is 1.96 on your z distribution, and I'll pull up our z table to show you that. So 1.96 negative 1.96. So let's go to our z table. So if we look at our z to infinity column to find our 2.5% when it's converted into a decimal, that's 0.0025. We see that, I'm sorry, not 0.025. I'm sorry about that. So this decimal here is associated with 2.5% on each end of the extremes of the distribution. So this z-score, 1.96, is really important. So make sure to memorize the z-score of 1.96 because that's where we start seeing statistically significant results when we work with z distributions. So once our scores are bigger than 1.96 on the positive side and 1.96 on the negative side, we start moving into statistically significant criteria or territory, if you will. So it's very, very important that we understand that 1.96, both on positive and negative side, begins our statistically significant threshold. So make sure to memorize that z-score. And that is the end of that PowerPoint. So make sure to email me with any questions that you have. If anything is unclear, make sure to watch the video about the practice problems. And yeah, email me if you have any questions.